Going over basic arithmetic operations. So, as we know, a plus b is just adding a amounts of a quantity plus b amounts of a quantity, which are arbitrary. You can assign any value to these, and getting a sum, which is just putting them together. That's all it is, and we learned that in elementary school. So that should be pretty simple. A minus b is slightly more nuanced because of negatives, but we'll get to that in a little bit. So a, the positive quantity, represents how much you have, and the negative quantity, or what's being subtracted, is how much you're taking away. So what happens when you're taking away more? Then you get into debt, which is why it turns to negative. So let's say we're taking 4 away. We can only really take 3 away logically in real life, but we can say you owe me one. So that's the logic behind that. Um, and ancient mathematicians understood subtracting negative. So if it's a minus, let's use a real world example because variables are arbitrary. So let's do 4 minus minus 2. How do you subtract negative 2? Well, ancient mathematicians understood this as debt. You're not really taking away something. Instead, you are taking away debt in a sense. So let's say you have $4 in a bank account, you have $2 in debt. In reality, actually that let's say we have $6, $2 in debt. So that means that we only have $6 in our bank account, but technically this $2 in debt makes us have $4 in the bank account. So taking away this debt, we're taking away a negative quantity, pulling it down. So that's why the subtracting a negative was defined as positive, because you're taking away debt. So when we use this in arithmetic operations, we're not actually denoting taking away negative, but instead ancient mathematicians just define this as adding two numbers, because I'm taking away negative, and although that's not the context, again, like I've said, in real life, ancient or mathematicians just denoted subtracting a negative as adding, and that's the logic behind it, using debt scenarios. Now we get to multiplication, which is, I would say, easier, but there is the commutative property, which I still haven't figured out a logical explanation to it. I mean, I can only use geometric, and I'm not sure if that's necessarily a formal proof using axioms, and obviously it's not. So 3 times 5 is having 3 amounts of 5, and having 5 amounts of 3 is 5 times 3. So the logic behind why these two are equal, after some digging, would be that if you drew a rectangle, which is what many ancient mathematicians did at the time, these are equal. They're just rotated 90 degrees, or how many rotations there are. However, notice that if we drew this out, or if we wrote this out, sorry, I'm still not sure why these are necessarily deemed to be equal. I'm just gonna guess that it has something to do with the rectangle formula, but I'm not too sure why this holds true every time. Well, I know why, but I can't really explain it mathematically, or not mathematically, algebraically. So there's an issue there. But multiplication just having 3 amounts of something, or a amounts of b. Exponentiation is a multiplied by itself the amount of times the power. A multiplied by itself the amount of power. Gosh. A multiplied by itself b times, or to the power amount of times. So if b is 2, then it'd be this. If b is 2.5, then it gets a little tricky here, because we'll do a 0.5. And that's simply what it's defined, because if you multiply two things together, and this is where the exponent rules come in, equals a b plus c. The logic behind it is that since it's repeated exponentiation, a is a repeated this many amount of times, dot dot, times b this many amount of times, or c this amount of times, sorry. Sorry, this should be b actually. And you can just add them together because it's still repeated exponentiation with multiplication together. So that's the logic behind that. Because technically they're the same term or the same base. So you can multiply them together. And that's because you could just add them because you're multiplying the same thing over and over. And again, an exponent is raising the base and multiplying it by itself over and over. And if you're multiplying another thing by the same term, the same base, then you can just add it because that's how many times it appears. So that's the logic. There's no script for this, so I'm going off my head, and it's a little difficult to voice what I'm talking about. Now we have a plus b times c. And this is where the distributive property comes in. You can write this as AC plus BC. In my mind, and I'm in high school, I was confused on why this worked. But if you put it into words of logic, it makes sense. Having A plus B of C is the same thing as saying, I have, this is one quantity, because PEMDAS, I guess, and you're multiplying it by C. So since the only modifier that is changing is the C, you can add these like terms, and that's the logic behind it. So you have A plus B C's, so you can either evaluate it or not evaluate it, which is the logic behind that. Now we get to division, and division is slightly complicated because there's many ways you could define division. They're not complicated in a sense, but they're a little bit complicated. Let me just put this as 0.25. So division is defined as breaking one thing into multiple even pieces. So let's say we have one whole cake here, and we want to split it into 4 even pieces. It would be that. Then we measure, I guess the area here of, or the ratio of this part of the cake to the whole cake, which is 0.25. But it gets a little tricky when we talk about reciprocals. And this is kind of why I wanted to make this video, because I wanted to get the logic out of my head. So 1 over k is 1 over 1/4. So how do we represent this logically? If we see how much 1/4 cake is, that means that 1/4 of the cake is only 0.25. But how do we see how big the entire cake is to that one piece, which is what the ratio is asking? How big this entire cake is to this one little shaded piece here. And the reason why this works, I believe, is because, or also k is 0.25 here, it's the ratio. So this is the same thing as a divided by b equals k, which is the context I was using all these arithmetic terms in. So, well, first you can explain this arithmetically. So if k equals a times b, or a over b, this is the same thing as 1 over k. And as you know in math, you can apply anything to both sides and they will come out the same. So 1 over k equals b over a, if the original terms were equal, obviously. So if like a is equal to c, you can do anything you want. You can square them, you can square root them, you can apply it to the third power, you can make them factorials, and they'll turn out the same if the original terms were the same. So the same logic applies here. You can just flip each side, which is kind of where the logic of getting the opposite ratio is. And I mentioned this because I was seeing a circle's circumference, and here I wanted to see how much time you could save by walking straight in the middle as opposed to walking around the outer perimeter. And as we know, this is 1/2 of a circle, so it would be 0.5 pi r, 0.52 pi r, so the 0.5 and 2 cancel out, leaving us r, and then this is just 2r, so we cancel out the r, giving us pi over 2, so the top part is pi over 2 times longer. So, flipping that, I did 1 divided by pi over 2, which is 2 over pi. And the logic is a little iffy, and I'm not too sure how to explain this arithmetically. I think it would be that we're seeing how many of these pieces, because 1/4 gives us how big this one piece is to the rest of the thing. So if we're dividing by 1/4, inversely, we're checking the division property or the division statement, and we're seeing how many 1/4 can fit into one. So that's kind of the logic behind it, because division is either defined as how many equal groups you can make. So this kind of defines that in this one we can make this many equal groups, and that is the logic behind ratios and arithmetic operations. This was like elementary level stuff, but I wanted to get this logic out of my head because some elementary things, like in elementary school, I thought the distance formula was really easy to figure out. But now it's like you have to find a formal proof. In fact, like um, Euclid, who discovered that a line is the shortest distance from 2 points. Like that's like common sense, right? If we have 2 points here, the shortest distance would be that, not curved or whatever. But there's rigorous proofs, and I kind of just wanted to get this out of my head. So yeah, this is like fifth grade level stuff, but the logic behind it is a little more complex. So